geothermal heat pump. Okay, and then this hydrothermal is actually one of the best method to convert geothermal energy into electricity. Hot dry rock method will be very expensive. Okay, and then geothermal heat pump is not expensive, but is low quality heat, mainly just for heating up the environment, okay, or to provide heat to the surrounding. Okay, so I remember we cover fresh steam power plant. Okay, so this is fresh steam where the steam is not hot enough up to the superheated steam. Then we need to do the separation. Separate between the steam and the water. Okay, and then secondly is called binary geothermal power plant. Binary geothermal power plant, I think, is the most widely used, which they have the lower temperature of 107 to 182 degrees Celsius. Okay, in the one proposed in Malaysia, Sabah, is also proposed to use the binary geothermal power plant. Okay, the word binary here is because they will use the secondary fluid to flash into the vapor upon heating. Okay, it means that they won't use the steam directly from the ground to run the steam turbine because the temperature is not high enough. So they have to use a secondary fluid which have the lower boiling point. For example, here it said that they use an organic compound with the low boiling point, which is the isobutane. Isobutane here can be the pentane, butane, something like this, the different type of isobutane. And this we use to drive the turbine. Okay, so it means that at this temperature, 107 to 182, we are not able to achieve superheated steam, but be able to achieve superheated condition for this binary fluid. Remember that to run the turbine, you must use the superheated steam. Okay, and this concept or this cycle, we can call it as an organic Rankine cycle. Remember that we see it the plant in Malaysia, they call it binary or RC technology. Okay, they use a binary cycle which use a secondary fluid, and this is the organic Rankine cycle or RC technology. Okay, and of course, organic because they are using the organic binary fluid. And then Rankine cycle is a thermodynamic process which is widely used for power plant, such as the coal power plant. They also use a similar cycle. We call it as a Rankine cycle. Okay, it means that how the process to release the heat energy and how the process to cool down and then to reuse the energy, the entire cycle. The name Rankine comes from, I think it's a inventor called Rankine, so that we name it as a Rankine cycle for RC. Okay, so the entire concept like this. You can see that the steam come from ground is actually in a closed loop. It won't actually release to a binary geothermal power plant. It should have the less environmental impact because you can see that whatever released from the underground, you actually pass through the heat exchanger. Okay, and then after you cool down, you pass back to the ground. There's no release. It won't release anything to the environment. Okay, so mostly you will be the safer. Okay, so at this heat exchanger here, heat exchanger is mean that where they change the heat, they transfer the heat from the hot steam or hot water, then transfer to this secondary fluid, which is the isobutane. Okay, once the heat transfer to the secondary fluid, they will boil and become the superheated steam. And then the superheated steam have the very strong pressure, which able to rotate the turbine. Okay, once the turbines rotate, then the steam have less energy and will be cooled down and recycled. Okay, but of course, I think we need a condenser or water cooler over here or cooling tower. It means that the steam, after you use to rotate the turbine, you must compress it back to the liquid form. Okay, how you want to compress this? Normally, we just use a cooling. Water is steam. Then we cool down the water, it will become. We cool down the steam, it becomes water. So same method can be applied here. Okay, so you have to do the cooling, and then reuse, and recycle the binary fluid. So the entirely is a closed system without any emission to the environment. Okay, and then the turbine here will rotate the electrical generator, and it will generate electricity which connect to the grid. This is a binary geothermal power plant. If we compare with the fresh, what's the difference is fresh using only the original steam from the ground, but binary they use the secondary flame. The reason is just because the temperature of the steam come up from the ground is not hot enough. That's why we need the binary flame. Okay, then we have third one. Third one is called combined cycle power plant, which means that there's a two turbine in this system. So there's a one turbine will be run by the steam from the ground, and there's a second turbine will run by the secondary flame. Okay, so it means that in this power plant, the turbine will be pushed for twice a cycle, every cycle. So supposedly you should have the better power output. Okay, but the problem is you must have a very high pressure geothermal steam resources. This is specially designed to generate the power from high pressure geothermal steam resources. Okay, so for the low pressure or not enough, not high enough, you only can do it one. Pressure push for the second time. Okay, this one is used for temperature not very high, but okay, but now the pressure is very high. Okay, so that when we design a geothermal power plant, we need to check what kind of the resources we have. We only depends on the temperature and pressure from the ground. Based on this, we can decide which type of system we want to use, which type of cycle we want to use. Okay. When there are non-condensable gas present in the geothermal steam, this technology provides higher efficiency, lower maintenance cost, and higher electrical output in comparison to conventional condensing steam power plant. Okay, for the conventional condensing steam power plant, this non-condensable gas actually is very harmful to the system. Not say harmful, it will reduce power output. Okay, by non-condensable gas cannot be condensed. Okay, what kind of gas cannot be condensed? So it means that these are the gases which are not easily condensed by cooling. For example, maybe nitrogen, maybe some carbon dioxide, like hydrocarbon, maybe some these gases, you are not able to condense it back into the liquid form in room temperature. Okay, how you want to convert the carbon dioxide into the liquid form? Or directly solid. So of course, in the room temperature, definitely we are not able to do that. Okay, so this one all we call it as a non-condensable gas, and this actually can strongly affect the power plant gathering system design and operation. Definitely will reduce the efficiency, because try to imagine that. Okay, maybe I take an example. You use the steam. Okay, the steam is a gaseous form. So inside the steam they have steam and this non-condensable gas. Okay, both of them will give the pressure to run the turbine. Okay, after you run through the turbine, we need to condense the steam together with all the gases. Okay, but because of this steam is mixed with this non-condensable gas, you are not able to fully condense all the gases into the liquid form. So in that case, the pressure created by the system will be relatively low. Okay, maybe this one. Okay, you can see that we do we have condenser over here to condense the water. So you condense the steam back into the water. But what if some of the steam cannot be converted into the water when you are doing the cooling, where you have this non-condensable gas? So it will affect your power, because now this gas will remain at this gas, and then you go into this turbine again and again. Okay, so it means that how we rotate the turbine, actually we need to create the pressure. You condense the gas into the water, okay, and then you go into the heating part, okay, and then you close the system, you heat it. So when the water boils, it will create a very huge pressure. But what if the water itself already in a gaseous form? Then definitely we will not create high pressure to it. Okay, you can see that. So that this non-condensable gas actually reduce the efficiency of the conventional steam power plant. But for this combined cycle power plant, there's one part over here. Always have this non-condensable gas compressor. Okay, so it means that they're able to separate this and they compress it back to the ground. So that for this system, it won't much affect the efficiency. That's why we said when the steam from the underground have this non-condensable gas, it's better to use this combined cycle power plant if it look on the efficiency. Okay, so this is the total cycle for this combined cycle power plant. You can see first we get the hot superheated fluid from the ground. Okay, we pump it out and have a separation because the temperature of the fluid is not too high. It can be converted to steam, but not 100% steam. It means that it's not yet reached the superheated steam. Okay, so in that case, you need to do separation. Separate the fluid, or we call it as a brine, and the steam. So the steam you use to run the steam turbine as level 1. So from here, you rotate the generator, you get the power output. Okay, and then secondly, this water is still very hot. You still can use this hot water or brine to heat up the secondary fluid. Okay, and then at the same time, this steam, okay, at turbine level 1, after it passes through the turbine, it will be slightly lesser in terms of pressure and temperature, but it's still hot enough to produce heat for the secondary fluid and convert them into the superheated steam. Okay, so by using the residual heat after the turbine 1 and the heat from this water, you're able to generate the secondary fluid, generate the superheated steam from the secondary fluid. Okay, you can see that. After that, you get the steam, superheated steam, and run the turbine at level 2. Okay, so after the secondary fluid run the turbine, then it have the less temperature and pressure. You have to condense them back into the liquid form. Okay, and then you can reuse this liquid for the second cycle. Okay, and the special part of this is they have the non-condensable gas. Of course, you can release these gases to the environment, but some of the gases actually not say toxic, up to toxic level, but some of them are greenhouse gas, something like carbon dioxide. Okay, and some of them are nitrogen. Okay, so they do not want to release anything to the environment, so they will compress the gas and then pump it back to the ground. Okay, so the full cycle of the combined cycle. So maybe it's for high pressure resources where you enough to use the steam for 2 times. Okay. Okay, the last type of this hydrothermal power plant is dry steam power plant. Dry steam is mean that superheated steam. So dry steam power plant is very rare, very powerful. So it means that when the steam released from the ground is already the superheated form. Okay, so it means that you must be at very high pressure and temperature. It means that highly pressurized geothermal vapor is used directly to drive your turbine. A much rarer fuel source, but the one used in the world's largest geothermal power plant at the Geyser in Northern California. And the superheated steam at 4 to 8 megapascal and the temperature of 180 to 225 degrees Celsius. And for this case, it has the higher thermal efficiency, which is around 20%. Okay. Okay, this is the dry steam power plant. You can see that the concept is the simplest. You don't need to do anything. You take the steam come from the ground and then directly use to rotate the turbine. Okay, and once the water is cooled down, you directly pump it back to the ground. Okay, no separation or no secondary fluid or whatever. The process is simple and cost effective. Okay, but only problem is this kind of resources is very rare. You are not always able to get it, at least not in Malaysia. We're not even able to have this steam power plant in Malaysia. I know that's a very good idea, but we don't have that kind of resources. Okay, and turbine will generate electricity through the electrical generator. Okay, so let's compare four types. From here, we have fresh, steam, binary cycle, combined cycle, and dry steam. Okay, so make a summary here. Fresh steam is when the temperature is not too high. You need to do the separation. Okay, and binary cycle is the temperature is even lower. Then even the separation is not enough. You need to use a secondary fluid. Okay, and then the third one is similar temperature as binary cycle, but it has, it's a similar temperature as fresh steam, but it has the high pressure. Okay, so that you can use this for secondary cycle. And then dry steam is the best, high pressure and high temperature. Okay, so if you want to run it, you have to consider first dry steam. Can you do it in dry steam? Okay, if cannot, can you do it in combined cycle? If still cannot, can you do it in fresh steam? And the last one is the binary cycle. Binary cycle is the lowest quality of steam power plant, but it's a widely available. Okay, so binary cycle is almost always our last resort. If even binary cycle cannot achieve that, then there's no way we can use the geothermal resources. But of course, as I said that binary cycle will use a secondary isobutane. But isobutane have many types. We have a pentane, we have a butane, okay? We have octane, and different type of this isobutane, we have different type of boiling point. Okay, so you can choose to use a lower boiling point, secondary fluid, in case of the temperature of the geothermal is lower. But most of the case, the lower the boiling point, the lower the density of the gas, so that it will not create enough momentum to rotate the turbine. Okay, so you use the steam directly. The steam is much heavier, much higher density than the isobutane. Okay, so a single push, it should give you the better power. Okay, of course you have to choose wisely lah. But same thing, the first thing we need to achieve is superheated steam condition. Okay, either to use the steam directly or use the secondary fluid. Okay, so hopefully you can differentiate between these four types of hydrothermal, geothermal power plant, hydrothermal. Okay, just look on this the Geyser geothermal complex, which is the largest geothermal power plant worldwide. Okay, in the world. So this actually commissioned in year 1960. Okay, a very long time ago. So actually the what to say the process the technology is matured since 1960. But why you still not see any log scale increment of the use of this geothermal power plant? This is because of that is not very widely available. Okay, like wind and solar, you can see that at recent 10 or 20 years, it grows very fast. But why geothermal didn't grow so fast? As I say, it's very good, and it has a very good technology since 1960. Okay, the reason is just the resources is very rare. Okay, and for this Geyser geothermal complex, the nameplate capacity is around 1,590 megawatt. Nameplate capacity, maybe other words we call it as a rated power. Okay, optimum power. And the capacity factor is 53%. And the annual net output is this amount, 6,500 gigawatt hour. And there is a number of views, 591. View is mean that the whole of the geothermal. Okay, and out of these 591, there are still 376 view which active. Okay, it means that there are some inactive due to some kind of the heat generation problem. Okay, maybe some kind of view when you collect the heat too fast. I mean that the flow is too fast. They will lose the heat. Sorry, they will lose the heat permanently. Okay, it cannot sustain the heat rate going up. So you have to design wisely so that it won't become that without the heat. Okay, some of them is because I think it's some kind of mistake lah. They based on the exploration, they make the assumption here there is enough heat. Okay, yes, but when they heat, yeah, the heat is there, but no water. Okay, so if you have heat but you have no water, you cannot do anything. Or maybe you have water, but after that, the water will maybe lost to the surrounding because water is actually sit inside the crack of the rock. But can the system hold the water is another issue. Okay. Okay, and then the maximum build depth is about 3.9 kilometers. And the geyser produced about 20% of the California renewable energy in 2019. You can see that this power plant actually contribute quite a lot for renewable energy for this California stage in the United States. Okay, so let's continue with the next one. Okay, after this hydrothermal power plant, we have next one called geothermal heat pump. This is just a pump. Okay, this is used for extracting heat from one shallow groundwater. You have the groundwater underground. Okay, then you have the pump, you have the pipe. Okay, you can see that you pump the water, the cold water, you pump through the hot water or underground hot water, and then you pump it back out. Okay, so the heat will actually transfer from the groundwater, hot groundwater, into the cold water inside the pipe. Okay, so the idea is just to circulate the cold water underground, which have the hot groundwater. Okay, but of course, this is not able to generate electricity, just for the cooling or heating of the environment. Okay, in Malaysia, you can do cooling. Okay, in a European country, you can do the heating. Okay, but cooling means that the groundwater is cold. Okay, now you want to cool down your environment. The environment is very hot, 35 degrees. Okay, and then the groundwater supposedly not exposed to the sunlight, then can be just around 25 degree or 23 degree. So in that case, I can pump the hot water, not hot water, I mean that water at the room temperature, maybe at 30 degrees Celsius, I pump it down. Okay, and then I pump it out and spray around my surrounding. So definitely it will reduce it cool down the environment. Okay, and according to research, this kind of system is 3 times more energy than the energy consumed in pumping the water. Of course, you will say you pump the water, you need energy. Okay, but the energy you use is just 3 times lesser than the energy you need to heat up the water. Okay, so this system is still worth for the operation, especially for the country like you have the winter. Okay, you can always use this kind of system. Okay, and then you can see that how you want to do the piping. You can do the horizontal loop, single loop, or point loop. It's totally up to you. Okay, depends on what kind of groundwater you have. So the concept is the pipe needs to stay in the groundwater as long as possible. Not say as long as possible because when the pipe is longer, the cost is also longer, and the size of the pump needed is also bigger because the pipe will create the resistance of flow. The longer the pipe, the bigger the flow resistance. Okay, losses in piping system lah. Okay, so that you have to arrange the pipe so that it's long enough to reach the thermodynamic equivalent with the underground water. Okay, so this has to be studied to check what is the temperature of the water you pump in, what is the temperature of the surrounding, how fast is the heat transfer rate, and then you can design how long is the pipe needed. Okay, but of course the concept is just to reach the thermodynamic equivalent. It means that the water inside the pipe and the water underground reach the same temperature. Okay, the idea is simple, so you can do it for cooling and heating. Depends on what kind of resources. Sorry, can you hear me? Because my neighbor is doing renovation.
Can hear, sir.
Then we just continue. Okay. This system is a energy cost saving. You just use 30% of the energy to pump the water, but you get much more heat energy. Secondly, it's environmental friendly. These do not have any combustion. You do not use any. You use less electricity. Okay, so you make it good for environment. You do not break any carbon dioxide, and this system have low maintenance, and which is a sustainable energy resources. A very simple mechanism, and it can give you very good heating resources. Okay. By Malaysia, I think we can do it cooling like Malaysia definitely. Okay, the next one is about the hot dry rock formation. We call it as HDR. HDR is okay. Maybe before that, aquifer are the easiest geothermal resources to explore for extracting energy. Aquifer is mean that hydrothermal, where we use the water. But this kind of the hot dry rock formation is dry. They do not have water, and it do not have much crack, so they cannot have to hold the water. Okay, you can see that this HDR means lack of porosity. Okay, so what you do, you have the very hot rock, but there's no water. Okay, so for this case, you need to supply the water. You cannot use the water from underground. You need to supply the water at very high pressure at the first time, at very high pressure to stimulate the crack. Okay, why you need to stimulate the crack? You need to increase the total contact area between the water and the ground with the hot rock. Okay, so you use a high pressure water pump underground and induce the thermal stress and cause the rock to fracture and create porosity. Mainly is to create a crack, not really to create a hole. Okay, so you create a crack, something like this. You stimulate high pressure water, create crack, and then now the water have better contact with the rock. Okay, so the heat transfer can be transferred very fast to the water, from the hot rock to the water. And once the water is hot, then you can pump out the hot water. Okay, and then you can do it as usual geothermal power plant, whether binary or direct usage or what. Okay, so this is the concept behind hot dry rock formation. Okay, its idea is good, but expensive because there's no water, and then they will face a lot of problem. Okay, let's look at it. What is the problem you possible to face? This is relative to conventional fossil fuels. HDR is a low-grade heat resources, require higher mass flow rate because the heat, the temperature that you can reach is normally not too high. Typical fluid production temperature about 200 degrees Celsius to 300 degrees Celsius are needed to maintain reasonable electric conversion efficiency of 10 to 20%. And this system is 5 times more expensive than hydrothermal system. 5 times more expensive than the 4 system that we studied just now. This is the hydrothermal system. And the power extraction needs to be planned properly to ensure sustainability. What I mean by planned properly is mean that do not know how fast the hot rock can regain the heat after you extract it from it. Okay, so that you have to study properly. The flow rate of the water cannot be too fast. If too fast, it means that the water will be too cold to supply heat to your system. Okay, and another problem is now you stimulate the crack, you create the crack. Do you think when you want to pump out the water, it will be any losses? Because if the crack is too long or too far, the water that you pump in actually will lost into the mud or into the soil. Okay, so this is always a problem for this hot dry rock formation. You want to maintain the water level inside. You are not allowed to keep pumping in the cold water, and then the hot water just flow to somewhere else. Okay, so you have to make sure that it can hold hot water. Okay, so this is something that very difficult to plan and something that out of our control. Okay, sometimes the crack will extend until somewhere underground water, so that whatever water will come in, it will just lost to the snoring. Okay, so this is a difficult part of this hot dry rock formation. Okay, so the next one, if this is a general one, okay, I think that's all mainly for the geothermal. Then let's talk about the general advantage of the geothermal resources. So first, this is renewable and non-depletable. I think nothing to explain here. It can be regenerated. Okay, accessible and well distributed, available close to none. But this is only, just now I said rare, but now I say accessible. Accessible in terms of heat, low quality heat. But you want to have the good quality one, I think it's very rare. Okay, something like in Malaysia, we always have a lot of hot water from the ground. Okay, in Setapak we also have. Okay, we always have the hot water resources for the entire Malaysia. Okay, so you can say that it's well distributed. And this is the emission free, no NOx. X refers to the number, can be 1, 2, 3, can be NO2, NO3. SOx, so same thing, can be SO2, SO3. And we have CO2 and particulate matter. CO2 is a carbon dioxide and particulate matter. But this emission free, you can see that I actually highlight the CO2 because not all the geothermal power plant have the zero CO2. CO2 is dissolvable in water. So if the geothermal resources itself have the CO2, then it will release CO2. Okay, depends on what type of resources you have. Same thing for NO. Some of the, SO, sulfur. Okay, some of the geothermal automatically contain SO. But this SO normally will not, the sulfur will not release to the environment in the gaseous form. It will become a nitrate, okay, and sulfate, which are in the solid form. So it dissolves in water, so it's still okay. This dispatchable for base load and peak demand saving. Okay, so output of this geothermal can be controlled easily. Okay, you no need to achieve what temperature, then only can have the maximum efficiency. No, as long as you use the steam, you already maximum efficiency. Because we are not creating the steam is come from the ground. Okay, for biomass, you need to maintain the certain temperature and pressure to produce superheated steam. But now the steam is not under control, the steam comes from the ground. So it means that you can control the output easily. And it can be for base load because this kind of resources is very reliable. It's scalable from 1 megawatt to 1,000 megawatt. Scalable is because one geothermal view normally can have one geothermal view normally can have only one turbine. So for example, for this you can see that there is a number of view which is 591. So definitely you can scale it to the size, to the output that you want. I have 591. Today I can run 10 view. Tomorrow I can run 20 view, 20 turbine, 50 or 100, depends on the demand that I need. Okay, so it can be easily adjusted. Okay, then this is flexible, generating of electric heat and co-generation. Co-generation is mean that you, other than generate electricity, you still use the remaining heat for environmental heating. Co-generation. And then this is this geothermal also have very small footprint, land conservative. Okay, maybe I show you first. This is a comparison of land usage for various type of power plant. You can see coal, solar thermal, photovoltaic, wind, and geothermal. Solar, as we say that we know that these are diffuse resources, so that we occupy a very big spaces just to generate a small amount of energy. Okay, and then you can see wind is much better, as you know that land below still can be used. Okay, and then you can see geothermal even smaller. You always need 404 square meter to generate 1 gigawatt hour of electricity. Okay. In terms of power output, it will be 3.5 square kilometer per gigawatt. Okay. So it's much better, like even better than nuclear power plant. You can see that nuclear power plant still need 20 square kilometer per gigawatt of power output. And solar is definitely the worst. Okay. Okay, and it's flexible and modular because you can adjust the output. And the system requires less maintenance compared to fossil fire power generation plant on the same capacity because you do not need a combustion chamber. You do not need a furnace to burn the fuel. Okay, and geothermal is always reliable and safe to operate. Cost competitive with the conventional fossil fuels. If you have that resources, definitely the price is actually competitive with the conventional fossil fuel. It can be very cheap. No need any government support. You can do that. Okay. But of course, there are also disadvantage of geothermal power. First, of course, is the location restricted. As I said, that resources is rare, so not everywhere you can get the same kind of resources. Okay, so it's only wherever you have, then you can use it. When wherever you don't have, then you cannot do anything. You cannot say, oh, I want to use solar. Everywhere you can do the solar energy power plant, but this is not as simple as solar. It's definitely very rare. Okay, the next one is the earthquake. Okay, geothermal actually something like this. When you run the geothermal energy, this geothermal energy run the risk of triggering the earthquake. This due to the actually when you do this, you drill a hole. Okay, you actually alter the earth surface. Okay, so this problem is more prevalent with enhanced geothermal power plant, which force the water into the earth crust to open up the fissure to gather exploration of the resources. So it means that the digging process will actually alter the earth surface, which will trigger the earthquake. But of course, same thing for the oil and gas exploration, you also have to dig the hole. Okay, so also the trigger the earthquake. But I think this kind of trigger is quite rare, not always happen, but it's happened before. Okay, the next one is a high capital cost. Mainly this capital cost it comes from the exploration and the digging of the hole. The hole you want to dig the hole of 3 kilometer depth is actually very costly. Okay, so if you can save the cost of digging, then it's a good hole. But I let the oil and gas dig the hole and then I use the hole. Something like this. I mean that oil and gas, they dig the hole, they extract all the oil and gas from the ground, and the hole will be actually abundant. Okay, so if I can use abundant oil and gas hole to retrofit it into these geothermal resources, then it's definitely I can save maybe 60% of the costs. But of course, where you have the oil, not necessarily you have the heat resources. This is a problem. Okay. And next one, sustainability. Yes, I know that geothermal is renewable and sustainable, but it also depends on how fast you pump out the heat. You need to maintain the sustainability of this geothermal energy by pumping back the water into the underground. Okay, so sustainable here refer to two types of sustainability. One is the sustainable of the heat. One is the sustainability of the water. Okay, you do not want to make the geothermal view dry. You need to always have the water. Okay, so the water must be sustainable, and also the sorry for that, and also the heat also must be sustainable. Okay, and then on the environmental side effect, this kind of this geothermal power plant actually will release the gas called radon. Okay, which is product of the decay of uranium, very low concentration, may cause lung cancer. And this radon is actually naturally available in the geothermal resource. As we know that, how come you can have the heat from the underground? it comes from the decay of the uranium. Okay, this decay of uranium release the heat, so that our Earth core is very hot. But again, the water sink into the underground, we are exposed to this kind of random, which is part of the decay of uranium at very low concentration. But actually, this kind of product will cause cancer. Okay, but you can see that most of the system is actually closed system. Then we do not have this issue because we not really release the gas to the environment. Okay, and some of them will release some of the CO2, as this CO2 is dissolved in the water. Some of them a very small amount, maybe just about, in average, just about 5% to the CO2 released from the fossil fuels power plant. Okay. So this one, land usage. Okay, then let's make a breakdown of the build cost by construction phase. So for the build cost, I mean the geothermal power plant, these are the costs that we have to pay for. Exploration, 20 to 30%. Drilling, 65 to 75%. So the expensive part, why make this geothermal expensive is actually these two things. When you want to find where is the location, and when you want to dig a hole. Okay, and then stimulation. Stimulation is where you stimulate the crack. Okay, you create the crack in the rock. This costs about 0 to 6%. 0 means that some of the cases you do not need to stimulate. Okay, so some kind of the rock already have enough porosity, have enough crack, then you do not need the stimulation. But I think most of them you still need to do something of stimulation to make a more crack, so that water can contact with the rock in more evenly. Okay, and then also the fluid distribution, 1-3%. How you plan for the water distribution in the underground. The view costs have the higher cost compared to oil and gas industry due to the larger view. Okay, sorry. Higher cost here refers to higher cost to make the view compared to oil and gas industry due to the large view diameter needed. You need to have the larger view compared to the oil and gas view. Okay. And these are the 3 laws of the geothermal economy. How are you going to plan? Of course, I can drill everywhere. I can dig everywhere to get the geothermal resources because the core is definitely underground. This depends on how deep you need to drill. Okay, so always remember these 3 laws of geothermal economy. Completed view cost increase exponentially with depth. Try to not dig too deep because it will exponentially increase the cost. Second law, power plant cost decrease linearly with the temperature. Okay, when you have the higher temperature, the power plant cost will be cheaper. It means that you will generate the same amount of, you will generate more power with the same size of the power plant. So I mean that per unit megawatt of power output, the higher temperature, the cost will be lower. Okay, but it will drop linearly. Okay, power plant cost decrease linearly with the temperature. And then the third law, as the resources quality decrease, the drilling cost will be dominate. Okay, so it means that when the quality of the heat underground is low, so the cost of the drilling will dominate the entire cost of the geothermal power plant. Okay, so but we also have the dilemma over here. If you look here, this is what we want to do. We want to comply first law, second law, and third law. But there's also have the dilemma over here. Okay, trade-off. I want to drill deeper to increase the temperature. Okay, as our power plant cost decrease linearly with the temperature. But when I drill deeper, I increase the view cost exponentially. Okay, so you always have to find the balance point and the optimum value. For example, this, you drill deeper, you decrease the temperature. So drill deeper is good thing, but you increase the cost, is a bad thing. Okay, and this lower the surface plant cost if you drill deeper. you need the less number of view to generate certain amount of power because you have the better temperature, better output per view. Okay, and then you will increase the individual well cost because you drill deeper, so the cost will be more expensive, and you will reduce the number of view needed to generate the same amount of power. Okay, and this one you drill the shallower to reduce the drilling cost. You don't drill too deep just to reduce the cost, but you raise the surface plant cost. You need more view to generate the same amount of power. Okay, you will decrease the individual view cost because of the drilling cost is lower, and you will increase the number of view needed. So you always have to check what's the size of the area I have. Okay, and then plan we want to drill, how deep you want to drill. You want to have high temperature or you want to have the low cost. You have to plan. Okay, we do not have a fixed answer for this. Maybe they have some kind of simulation you can do the best depth to generate 10 megawatt of electricity. Okay, maybe they have some kind of simulation can do that. Okay, and these are the estimated drilling cost versus depth. You can see that actually it increased exponentially. Okay, so here is the hot rock. So you see that when hot rock, normally you need to drill deeper. Okay, and conventionally hydrothermal is all here. Okay, hot rock normally is too deep, and it somehow the water will not reach that location, that area. Okay, so normally if you have a water at the location closer to the Earth's surface, we won't go and expose. We won't go to expose the hot rock formation. Okay. So these are the temperature profile of the inner Earth. I think we discussed before. I think okay lah, we showed you before. So we are always in the first layer only, retrosphere only. Okay, and these are the current limitation of the drilling technology. So first, drill cost still exponentially with depth, I think okay. And maximum depth capacity to 12 kilometer. Okay, now we have the maximum depth we can do is 12 kilometer. I think the hole is near to the, in Russia, if I'm not mistaken. Okay, but they not make it for anything, not for, they just have the idea to drill as deep as possible. Okay, something like they're making an experiment and see how deep they can reach. Okay, so then they reach this 12 kilometers. Okay, why you cannot reach deeper? Okay, when you reach deeper, the temperature will become higher. Okay, so what happened to your drill bit and drill hole, the bore head? You have the less strength. It won't be so hot anymore because temperature increase. So that it make you not possible to drill even deeper. Okay, so this is a problem mainly. Okay, so what are the limitations? First, because of the material that we use for deeper and deeper, you're getting softer, very soft. Okay, and next is the borehole stability. The hole is very deep, 12 kilometer deep. How you want to maintain the hole and avoid it to collapse? This is also one of the problems. So depends on the structure and material of the hole. Okay, in it's rock, then normally it's quite easy to maintain the stability. But what if just a soil or maybe some kind of sand, then definitely you are not able to maintain the stability of a borehole. Okay, and then we have this lost circulation mud is still a big problem in some formation. This mud is actually fluid that they use to remove the during the beast. Okay, you drill the hole. Of course, you have to break the rock or you want to have the mud you want to remove. Okay, so they use the circulation mud. But the problem is circulation mud may not return to the Earth's surface. You put in the circulation mud, but the circulation mud will somehow move to somewhere else due to the crack on the rock or other opening. Okay, so this is always a problem when you put in the mud, but the mud missing. Actually, it's not the real mud, it's some kind of liquid to remove the debris from the ring. Okay, to carry out the cutting debris out from the hole. Okay, and the debris have to be improved to increase the penetration rate, but the entire system is still prone to bit wear or crushing as a primary failure mechanism. Bit wear, when it's getting softer and softer, it will wear very fast, and it will crush when the rock is too hard, harder than the ball head, drilling. Okay, so that what we can do is, as an engineer, we try to improve the limitation here. Okay, we can study how to maintain the borehole stability, how to increase the borehole stability, maybe new technique, and how to maintain the circulation mud, and how to make the drill bit even harder and have the less wear and less maintenance needed. Okay, so if we can improve this, maybe we can get better resources in the future. This is what we can improve. Okay, but I think the hole that they did in 12 kilometer depth already more than 50 years, but now no one try to dig deeper, even we have the better technology, because actually nothing we can get lah. We dig deeper. We already know what we have underground. We dig deeper for what? To check what? To check something else. Okay, just to checking, you need to spend a billion ringgit, so it's not worth for the investment lah. Okay. Okay, this is another option to use the abundant view from the oil and gas field. So according to the research, the US United States have 2.5 million abundant oil and gas field, and some of which are a few kilometer depth. So if this view can be retrofitted with a new self-containing pipe with a pipe that could allow them to function at geothermal view. So geothermal view function is I pump in the cold fluid, and then it will pump out the hot fluid for me. Okay, so this is the idea here. You can see injected fluid, cold fluid from the side. So this side will contact with the rock at the surrounding. So the heat will transfer from the surrounding, from the underground, into the hot fluid inside. Sorry, into the cold fluid inside. Okay, so once until the fluid is hot enough, it can go through the middle pipe. Okay, and this will transfer the hot fluid to the earth surface. Of course, you have to do the proper insulation. Okay, because you do not want the hot fluid that you want to transfer out being cooled down by the fluid that you transfer in. This is a problem. Actually, it's not easy, I would say. Okay. The idea is there, but I think no one actually used this before. The idea is to use the abundant hole, but because of the cost, it's not really implemented. We still have the better resources out there in terms of wind, in terms of solar. Why we need to go and retrofit this kind of the view? Okay, but the idea is possible. How do geothermal power plant compare to fossil fuels fire power plant? Okay, if I compare with geothermal power plant, you can see that both of them use steam to run the steam turbine. But how is comparison? Okay, first of course, a geothermal is renewable, and there is no burning. No burning take place, so there's no smoke, no emission, or very less emission compared to this fossil fuels power plant. Okay, and this geothermal power plant and fossil fuels power plant, both of them will emit like hydrogen sulfide, sulfur dioxide, and some particulate, and also carbon dioxide, of course. But the amount of this emission from geothermal power plant is very minimum, because these are the material resources naturally available in the water. Okay, and what else about this? Okay, but of course, not all the geothermal power plant will release emission. Okay, maybe if you look on the four type of the power plant over here. We have 4 types. We start from flash. Yes, this type definitely will release it's not a closed system, it's an open system. So have the possibility to have the emission. Binary, completely closed system. So this one no emission at all. Combined cycle, there's emission. Okay, fresh dry steam, there's emission. So only binary cycle will have the zero air emission because it is a closed system. The steam from underground, the hot water from underground will not expose to the surrounding. Okay. Okay. Then what else? I think we have always say that it's much lesser lah. But another thing is this geothermal power plant normally will contain the hydrogen sulfide, hydrogen H2 and sulfur. Okay, which molecule dissolved in many geothermal water in variable concentration. It means that in different concentration. And the sulfur in this hydrogen sulfide will bind with the oxygen to form the sulfide. Okay, and these sulfur compounds are naturally occurring in hot spring, and the source of the characteristic of eggy odor. You feel that they smell like an egg. Okay, and the sulfur. So as the hot spring going deeper, the odor, the smell will be stronger. The sulfur smell. So actually you can define the depth of the hot spring based on the smell of the sulfur that you know. If your nose is good enough, you can separate, you can differentiate the level of sulfur. Okay. Okay. Can geothermal energy help to reduce the global warming? I think this definitely yes. Okay, because you reduce the amount of carbon dioxide released to the environment. So of course, it will improve the global warming. Also, so it will reduce the global warming. Okay, rather than use the fossil fuels. And in summary, geothermal energy application based on its temperature, it has different value and possible application. At base load, it can be non-seasonal resources with high capacity factor. Okay, moving from location specific to ubiquitous resources. So it means that can be accessed everywhere. But this one, I think, is just refer to the low energy heat. Huge potential, but technically difficult. Huge potential means that technically you can get geothermal resources everywhere. This depends on how deep you want to drill. Okay, this is what we have that technical difficulty on drilling deeper. And geothermal resources always have the low first law efficiency and good exergy efficiency. First law efficiency here refer to output over input. Okay, so based on this amount of output from the geothermal resources, only a very small amount of power output you can get. Okay, input from the geothermal, and then, okay, maybe you talk about the turbine. The input should be from geothermal fields, and then the output will be electricity. So the amount of electricity you get compared to the amount of energy you have in the geothermal field is actually very less. So make the first law efficiency very low. Output over input will be very low. But it always have the good exergy efficiency. Exergy efficiency refers to the output, actual output, divided by the maximum possible output. Okay, so later we'll cover it in the Exergy chapter for more detail for Exergy efficiency, or maybe you can call it as the second law of efficiency. And most cycle can be used in cogeneration. Most of the geothermal resources can be used in cogeneration. It means that the residual heat can be used for heating purposes. Okay. Yeah, this is the capacity factor for renewable energy. So you can see that geothermal have the highest capacity factor from 86 to 95%. It means that 86, okay, let's talk about 95%. It means that this geothermal power plant able to produce the rated power almost all the time. 95% of the time. So it's definitely very, very good. Okay, you can see the biomass 20 to 90, depends on the resources that you have used. Hydropower 40 to 50. Some of the time you need to use to accumulate the water. You cannot run the turbine for all the time. Okay, CSP stands for concentrating solar power 25 to 75. Okay, and then wind 27 to 43, wave 1540, tidal 3040, and PV is the lowest 15 to 22. Because the solar energy, the sun is not always shining. Okay, and then next is about this in the morning, in the afternoon, because the long distance travel through the atmosphere, the photovoltaics, the solar irradiance that reach the photovoltaics will be much lower than 1000 watt per square meter. Okay, remember that the capacity of the photovoltaics is calculated based on the standard test condition, 1000 watt per square meter. But actually you can see CSP and PV are both solar panel. Okay, but why CSP have the better output than this? Just because the way they calculate the capacity is different. Okay, this one they calculate based on the standard test condition. But this CSP, because of concentrating solar power, they concentrate all the solar power into one point. They are no longer using the standard test condition, because definitely the amount of solar irradiance that reach the solar panel will be more than 1000 watt per square meter. So they have their other standard. Okay, so in other words, they have the other way to calculate the rated power. Okay, so to make it much higher than PV. Okay. Okay, let's continue. These are these are comparisons of different type of energy resources in terms of safety and in terms of the impact to the surrounding. So we look, coal have the most accident, okay, and followed by oil and natural gas and biomass. All of these are combustion. So as we know that combustion normally will create a lot of problem in terms of the emission, explosion. Okay, and these coal, oil, natural gas, and biomass actually even more cause more death than nuclear energy. You always think that nuclear is very dangerous, it causes a lot of accident and air pollution. But actually, in this arrangement, you can see that coal, oil, and natural gas is actually the main power plant that cause the death. Okay, and then solar is safer, I would say that. Solar photovoltaics. Okay, and followed by wind. That's why it's widely used. Safe and clean. You can see if we compare the safe and clean, both of them are at very low level. Okay, solar is the safest. Okay, the best renewable energy in terms of safety. You can see the photovoltaics, you can build one at the home. But are you able to build the rest of the power plant at home? Normally will be very dangerous. But solar, because the system is too simple, to make it very safe. Okay. And then in terms of the impact to the surrounding, greenhouse gas emission, same thing. Whichever have the emission, whichever have the combustion, release a lot of greenhouse gas. Okay. And then biomass is have a range lah. Okay, because they also have combustion. And yes, I know that biomass is carbon neutral. If compared to fossil fuels, it's still better. But if compared to other type of renewable energy, it's not so great. Reason is, yes, eventually the biomass will convert into the H2O and CO2. But everything is a matter of time. You let the microorganism to decompose it, it will take maybe years. But if you burn it, you just take a few minutes to fully convert them into the carbon dioxide. Okay. And then the hydropower. Yes, we always say that hydropower is not clean, but you can see that in terms of gas emission, it's only 34 tons. But now they claim that hydropower should be more than the coal power plant, just because of it reduces the oxygen generation. Okay, all type of the power plant will have less impact to the oxygen generation. but only hydro, because you build a dam and reservoir, then it reduces the oxygen generation. Other than carbon dioxide you generate, you still reduce the amount of oxygen you generate. So end up with, you do not add on the carbon dioxide, but you change the share of oxygen. Okay. And then nuclear, also very less greenhouse gas. And wind and solar is quite similar, but wind is lesser than solar. Okay, because why? Okay, we know that nuclear, wind, and solar, the operation will not release any carbon dioxide. Okay, but other than operation, we still have to consider the upstream and downstream effect. Whenever you develop, you manufacture the solar panel, the wind turbine, and nuclear power plant. This amount of energy you need. Okay, and most of them you need a fossil fuel energy in general. Okay, so solar and wind, I think I consider as the best widely available and safer and greener. Sorry. Sorry, geothermal is not here because geothermal is quite small. The share of the geothermal is quite small, including the wave and tidal. Okay. Okay, I think that's all for the 7 type of renewable energy that we cover in the syllabus. Next, later we can go into the Exergy. Okay, before we take a short break, any questions on the geothermal chapter? No issue. If no question, then maybe you can take a 5-minute break. Come back at 12:15, and we will continue with the Exergy chapter, the last chapter for renewable energy. Okay, see you later. Okay, welcome back. So let's continue with the last chapter, Exergy. And for later, I think I sent before in the classroom. You can check the Steam table. I will share again after the class. So starting from next classes, you have to bring your Steam table. If you have the hard copy, should be better. Okay, mechanical, mecha, if you're already clear about what Steam table. Okay, let's continue. So first, we talk about what is meant by Exergy. You see your title, you have the Exergy and renewable energy for mechanical and mechatronics. Okay, so this Exergy is very, I think not much people using this word, but the idea is a property to measure the useful work potential. We don't use the word Exergy to measure the work potential because some of the energy cannot be converted to power due to some kind of environmental situation. Okay, so this Exergy is defined as the maximum useful work that can be obtained from a system at a given state in the given environment, and it will be associated with the environment and not conserved. Remember that energy is conserved, but Exergy is not conserved. Once wasted, it can never be recovered. Okay, what is the Exergy mean in general? Maybe I can give you an example. Okay, let's say I want to have an energy generation for a cup of hot water. Okay, so in that case, I want to generate energy. I need to make the heat transfer. Okay, so the hot water is very hot. Okay, surrounding is very cold. So the hot water, the energy from the hot water can transfer to the surrounding. So we have the heat transfer, net heat transfer outward. Okay, so this heat transfer can be used as energy, useful energy. Okay, but what if, yes, you have the same cup of hot water, but the environment is the same temperature as the hot water? So what happens? They will have the zero net energy transfer. It reaches the thermodynamic equivalent. Okay, so in this case, if I tell you that I have a cup of hot water, can you tell me how much energy you can get? No, you cannot do anything. You cannot tell me how much exactly energy you can get unless I tell you the environmental condition. Okay, that's why they come up with this definition called Exergy, where you can estimate the amount of maximum possible useful work can be done based on this situation, but not just by the temperature of the system. You still need to know the pressure, temperature, and variable of the surrounding. Okay, so it's always Exergy is always associated with the environment and surrounding, but energy not. Okay, so whenever to check the amount of maximum useful work can be done, you have to use the term Exergy, but not Exergy. So you can see the title here, good think Exergy, but not energy. I know that we have the energy, but you can convert the energy or transfer the energy is another issue. Okay, so then we use the term Exergy. And this Exergy, once wasted, it cannot be recovered. Okay, what's mean by wasted? Wasted is mean that the energy convert from one energy to another energy, which have the less useful. Okay, what is useful and not useful? Useful is mean that it can easily convert to other type of energy. For example, electricity. Electricity is the most useful energy we have in the world. Okay, secondly, maybe mechanical energy, rotation or motion. Okay, then the less quality energy normally is about heat. Okay, yeah, but quite difficult to use heat directly. You always have to change it to mechanical or electricity. Okay, so this is the definition of Exergy. So energy is conserved because energy just changed from this form into other form. But Exergy, once you change from this form to other form, then it cannot be useful anymore. Okay, that's why we say Exergy is not conserved. Okay, so this Exergy defines the upper limit on the amount of work a device can deliver without violating any thermodynamic law. from initial state to that state in a reversible manner. Okay, I later will explain what is that state, what is the reversible. Excluded all irreversible process or losses. Okay, so initial state is the beginning of the process, and that state is the state where equivalent with the surrounding. The system cannot transfer any more energy. We call it at that state. Okay, reversible is mean that you can convert to point, you can convert from A to B and can fully convert back from B to A. Okay, but this is just an ideal case, which never happened. Okay. Okay, let's look on the example of Exergy. When you use the energy to heat our home, we are not destroying any energy. We are mostly converting it into the less useful form of less Exergy. As I explained to you just now, electricity is very good Exergy. Okay, but heat is very less Exergy, although the energy amount is the same. Okay, and number two, 100 joule of heat would correspond to less Exergy than 100 joule of electricity. Okay, actually how much Exergy is present in 100 joule of heat would depends upon the temperature, pressure, chemical composition of the system, as well as the surrounding. However, 100 joule of electrical energy corresponds exactly to 100 joule of Exergy. Okay, it means that we are not able to use energy to differentiate the quality of energy. That's why we use the word Exergy. Okay. So why we need to study Exergy? Why not we just study energy? Because it can be used for the system optimization. By analyzing the Exergy destroyed by each component in the process, we can see where we should be focusing our effort to improve the system efficiency. It can also be used to compare the component of system to help to make the informed design decision. So you can check whichever part have the low Exergy, then you can do the improvement. But for example, we cannot just simply use the efficiency, okay? Because they always have the upper limit due to the environmental situation. Maybe I give you some, let's say I have the water at 100 degrees Celsius, hot water at 100 degrees Celsius, environment at 25 degrees Celsius, okay? So how much energy you have in 100 degrees Celsius of water? You should take 100 degrees Celsius minus the lowest temperature possible is actually 0 Kelvin, negative 273 degrees Celsius. Okay, and you measure the range, and you will know how much energy content in the water. But if you check the Exergy, it's totally different. What is the maximum possible temperature the water can reach? We are up to the environment temperature only. You put it there, it will drop until from 100 degrees Celsius to 25 degrees Celsius. It will never drop to negative 273 degrees Celsius. Okay, only at negative 203 degrees Celsius or 0 Kelvin. That is the point without energy. Okay, all the atomic bonding is static, no motion. But we cannot reach that. So how come you can count the energy that we can never be extract? Okay, so when we check for the Exergy, we only check from the temperature of 100 degrees Celsius until the surrounding temperature of 25 degrees Celsius. After that, it's useless because it will reach the thermodynamic equivalent with the surrounding. Okay. Then we talk about the dead state. Dead state is mean that the state is equivalent with the surrounding. The system and the surrounding is in the equal temperature, equal pressure, and whatever, everything equal. So that you will not able to have any net energy transfer. So that you can see for this dead state, we call it as a 0 Exergy. Okay, but it still have the energy, but just cannot make any transfer because the surrounding also have the same energy as the system. Okay, you do not have the potential difference to transfer the energy. Okay, and at the temperature and pressure of its environment, no kinetic energy, of potential energy relative to the environment, chemically inert, so no chemical reaction possible to happen, no unbalanced magnetic, electrical, or surface tension effect, no any force that possible to happen, and no more work can be done. And this one we call it as a dead stage. Okay, something like maybe we can talk about electrical circuit. How you want to let the electron to flow? You need to have the potential difference or voltage difference between two points. What if these potential difference are exactly the same? Even though you have a lot of electron, but do you think the electron will flow? The electron will not flow. Because both sides have the same amount of electron, same amount of charge. But you cannot say there's no electron. Yes, there's a lot of electron, but this is the one to flow because of the balance, because of the equivalence of the system. Okay, this is why we study Exergy. Okay, then after the concept, then we go to some theory and calculation. Then we need to know one term called reversible work. Reversible can be reversed. Okay, the reversible process is actually defined as a process in which the system and the surrounding can be returned to the original condition from the final stage without producing any changes in the thermodynamic properties. Okay, so it means that you can convert back into the original position without changing anything. So it means that losses lah. So whenever you have the reversible work, it means that 100% of the energy is converted to the work. And from the work, you can convert 100% of them into the energy. But is that possible? Normally, whenever you convert, you lost 20%, 30%. Okay, so that reversible is just an ideal case. Okay, yeah? That's why we call it as a reversible work. It means that you have the 100% of efficiency. The useful work, okay, the maximum amount of useful work that can be produced as a system undergo a process between a specific initial and final state. The useful work output obtained when the process between the initial and final state is executed in a total reversible manner. So if I want to check to measure the reversible work, I can check the Exergy in the state 1 minus the Exergy at the state 2. How to measure this? Okay, Exergy at the state 1 is mean that Exergy of the system before the process. Okay, Exergy of state 2 is the Exergy of the system after the process, at the end of the process. So the process can be just a heat transfer. The temperature of the water at 100 degrees Celsius and the temperature of water at 40 degrees Celsius, that's it. So you calculate the Exergy inside water of 100 degrees Celsius minus the Exergy inside the 40 degrees Celsius, then you should be able to measure the total maximum possible output can be done by the heat transfer. We call it as a reversible work. Okay. Again, this is the ideal case. But why we use the ideal case? Because we are trying to measure the potential of the system. We are not really want to check the actual power. Actual power is something that fixed and you are not able to improve anything. So you need to always know that maximum possible power, which we call it as a reversible work. And then you can compare this reversible work with the actual work. And then you can see how much you can do the improvement. Okay, if the actual work already very close to reversible work, then don't waste your time to do the improvement. Or even the actual work already exactly the same as reversible work, as an engineer, don't do anything. I know that you still have the energy inside, but it's already close to the reversible work. No point to do the improvement because you are definitely not able to achieve that. So you are trying to do the improvement at which process where the difference between the actual work and the reversible work is very huge. So that they should have a very big room for improvement. So we improve from that side. Then you make your work easier and faster. Okay, and then you can easily achieve your target. Okay, so make use of the comparison of reversible work and actual work. Don't simply, I want to improve this process, but I don't know what is the maximum possible value. I just want to improve it. Okay, don't do this kind of assumption. You have to check reversible work and actual work. You only decide whether you want to do the improvement or not. Okay. Okay, the next one, okay, this is a heat engine. This is just some introduction to heat engine. What's the engine do? You put in the electrode, it give you mechanical work. Okay, so heat engine is mean that you give heat into the engine, and the engine will give you the mechanical work. Okay, so act by transferring energy from a warm region to a cold region of space, and in the process converting some of that energy to mechanical work. In the process of going through this cycle, the system may perform work on its surrounding, thereby acting as a heat engine. Okay, you can see that heat engine, you supply the heat, it gives you the mechanical work. And this is another term called heat pump. Heat pump is the totally opposite. You supply the work, heat pump the heat. Okay, so it means that you supply the work to increase the temperature of the system. That's called heat pump. But I don't cover here because it's not part in the syllabus. We normally study on heat engine only. So I make a slide for this for heat engine. Okay. So now we need to study oh no, very noisy. Okay, we need to study the form of Exergy. Okay, form of Exergy can be a lot. And kinetic energy and potential energy is one type of the Exergy form. You still have the change of internal energy lah, Exergy destroyed lah, change of entropy, enthalpy, and so on and so forth. Okay, we'll go through one by one. And remember, you want to calculate the Exergy of the system, you need to combine all forms of Exergy. Okay, so first one is a kinetic energy. When direct forward, we know that kinetic energy equal to 1 over 2 mv squared. Just stop me if you don't understand. We know that kinetic energy equal to 1 over 2 mv squared. Okay, and then the unit will be joule. But for the study of Exergy, we always use the amount of Exergy per kg of the system, of the water, of the steam, or something else. Okay, so you per unit kg, this m will be automatically equal to 1 kg. So I can say that Ke will be equal to V squared over 2. And then you can see that the joule now already changed to kilojoule. So it means that you need to divide by 1000. Okay, so this is how we calculate the kinetic energy in terms of kilojoule per kg. Okay, and this kinetic energy is independent of the temperature and pressure of the environment. It's just measuring the velocity of the system. Okay, the next one is the potential energy, and same thing, potential energy mgh. Okay, and m equal to 1. So you have only gh, but of course the height they use that. Okay, but similar. And then same thing, you convert from joule to kilojoule, I divide by 1000. Okay, so again, this potential energy is independent of the temperature and pressure of the environment. So we have kinetic energy, we have potential energy. These are the two forms of Exergy that we have. So now we go to the next one. Okay, no, let's try this example. A windmill with 12 meter diameter rotor. This rotor is 12 meter. Is to be installed at the location where the wind blowing steadily at the average velocity of 10 meters per second. Determine the maximum power that can be generated by the windmill. Okay, so same thing, you can do it properly. As we know that this wind power 1 over 2 m dot v squared, according to the chapter in the wind energy. 1 over 2, 1 over rho v cube, rho a v cube. Okay, then you can get the power. Rho is 1.18. Area, strap area, I r squared. Velocity 10 meter cube. Okay, but this will give you the answer in terms of what? Okay, what's the answer you get? Guys, 65. Okay, so this measuring the maximum power according to the kinetic energy. I think not really difficult. Okay, we can just skip. Just to calculate the power. Okay, then we talk about the surrounding work. Other than the work to the system or work from the system, we still have one term called work to the surrounding. Work to the surrounding is something like the work done by work producing device. Okay, sorry, the work done by the work producing device not always entirely in the usable form. For example, when the gas in the piston cylinder device expands, part of the work done, the gas is used to push the atmospheric air out from the way of piston. Okay, you can see that the figure at the right hand side. This is the piston. Okay, and then whenever the system V1 expands, okay, it will move this piston head, the cylinder. Okay, this cylinder will move it upward. Okay, and then it will transfer the movement of cylinder to move the engine or move your car. Okay, but at the same time, this system have to push against the atmospheric air. Maybe you think that the air is very light, the pressure is very less, so no need to calculate. Okay, maybe the surrounding work can be very small, but in some of the case, especially the small amount of pressure, small amount of power, you still have to consider work done to the surrounding. Okay, because the atmospheric pressure is pressing on the piston. So you want to move the piston, you have to work against the atmospheric pressure. Okay, so how to calculate the work done on the atmospheric pressure? So as we know, work done equal to force times distance. It's a general equation. Okay, and from here, force here, you can write it in terms of pressure. Okay, pressure, what is pressure? Pressure is a force times area. So if you want to guess force is pressure times area. Okay, and times R. Okay, the area here will be the cross-section area of the piston. The R here is how far it moves. Okay, so based on this, I can measure the work done to the surrounding by PO, V2 minus V1. And the PO is not the pressure inside. You want to work to against the surrounding, so it should be atmospheric pressure. Okay, and V2 is the volume after, and V1 is the volume before. So this V2 over V1 actually is also equivalent to the cross-section area multiplied with the change of the location. Okay, so this one we call it as a surrounding work. And only you need to push against the atmospheric pressure, you need to consider the surrounding work. For some of the case, something like the rotation in the tank do not actually expose the surrounding, then no need to calculate the surrounding. Okay, later I'll show you the sample. The work done by this surrounding or against atmospheric pressure has significant only for systems which have the volume change during the process. For example, systems that involve moving of the boundary work, which is piston cylinder. You can see that this one, the figure at the right hand side, this is a piston in our car engine. Okay, so we have 4 pistons over here. So you can see that this piston when the combustion at the third location, when the combustion of the fluid inside the cylinder, it will push the piston downward and rotate this to move your car. Okay, but at the same time, there's an air pressure outside the atmosphere that you need to overcome. Okay, and this is the work done to the surrounding. And of course, some of the case it can be represented as a gain other than loss. Loss is mean that now atmospheric pressure is pressing on the piston. Okay, atmospheric pressure is pressing on the piston. Now your movement is downward. So this atmospheric pressure will actually against your work. So it's actually minus, it's a losses. Okay, but for example, for this case, compression stroke, you want to compress the air inside. Okay, so this piston moving upward and atmospheric pressure doing the same thing, pressing at the same direction as the motion of the piston. So this is actually gain. The atmospheric pressure help you to push against the piston. Okay, so surrounding work can be represented as gain or a loss. Depends on the direction of the motion. And the work done by surrounding or against atmospheric pressure has no significant effect for cyclic devices. And system which boundary remain fixed during the process, such as the rigid tank, and steady flow device such as the turbine, compressor, nozzle, and heat exchanger. Okay, you can see that rigid tank. The blade is rotating inside to give you the power, or you transfer the power to the rigid tank. But how you create how the atmospheric pressure against you? You are just rotating. Okay, so it won't create any atmospheric pressure. Okay, so we can say we can ignore the work done to the surrounding for this kind of system, rigid tank, cyclic device, and steady flow device like turbine, compressor, nozzle, heat exchanger. For this turbine, same thing. This steady flow device have the continuous flow. Okay, and do you think that the atmospheric pressure will make any difference on this? Because you can see that the water flow inside and flow out, and inside of this is full of water. So how the atmospheric pressure actually apply to the system against the motion? No, the motion is inside. The motion of this turbine is on the blade, and the blade is fully covered by the water. And then definitely the air, the atmospheric air will not have any impact, will not create any resistance to the movement of the blade. Okay, so we can ignore the work done to the surrounding for this kind of the system. Okay, so in other words, surrounding work only to consider in piston cylinder, I would say that, or something is expanding, something like balloon. You are blowing a balloon, then you have to consider the surrounding work. Something like the volume is increasing or decreasing, something like this, distance moving, then we only have to consider the surrounding work. Okay. And then after that, we also have another term called useful work. As we know that some of the energy is used for the surrounding work. So the useful work will be the total work, actual work minus the surrounding work. Okay, very direct lah. It means that previously the work done by the system is not 100% convert to the useful form. Useful form is mean that to move your car, to do the work that you want, you desire. Okay, so this equation to get the useful work. Then we talk about the important thing called irreversibility. So just now I talked about the reversible work, which the work can be reversed back to the original condition. And of course, this is just the ideal case. And most of the actual situation, they have this term irreversibility. They have some part of the system, some part of the process is not able to reverse. Okay, and this can be calculated based on the difference between the reversible work and the useful work. Okay, it means that whatever losses, we can count it as a irreversibility. The losses can be the internal resistance, can be external resistance, can be something else. Everything is losses. Okay, because you are not able to convert back. Okay, and this irreversibility is a wasted work potential or the lost opportunity to do work. Okay, let's say I have hot water. The hot water have 100 joule of energy. Whenever I convert to electricity, it left only 40 joule of energy. Okay, so this 60 joule of energy is actually lost. many reasons why it's lost. Okay, and that is all considered as the irreversibility of the process. Okay, because the electricity missing, lost due to the process. And when you want to convert back, you only have the 40 joule to convert back to the heat from electricity. Okay, 60 joule definitely gone already. Yeah, so that's what we call as a irreversibility. This irreversibility also equivalent to the Exergy destroyed, because now we convert from 100 joule of hot water into the 40 joule of electricity. Okay, so it means that this 60 joule is destroying the potential of energy, or destroying the Exergy. Okay, so you remember irreversibility equal to losses and also equivalent to the Exergy destroyed. And for a heat transfer system, the Exergy destroyed or irreversibility can be calculated based on the change of entropy. Okay, so you can base on this T naught S generation. T naught is the temperature of the surrounding. S generation is the entropy generation generated during the process. Okay, I mean for heat transfer process. So that we are using losses inside the heat transfer process. Okay, so these losses in heat transfer process is not counted. The resistance or the friction or whatever. This is everything internally inside the heat transfer process. Later we'll go through what kind of losses you can experience here and what kind of process will generate the entropy. So first we need to know what is the entropy. In layman term, entropy is a measure of the number of microscopic configuration that correspond to a thermodynamic system in the state specified by a certain microscopic variable. Okay, it can be understood as a measure of the molecular disorder. How disordered is the system? Okay, within the microscopic system. You can see that for solid material, we have very low entropy. All the molecule is arranged nicely, no disorder. Okay, but for the gases, they have a very high disorderly. You can see that all the molecule is random. Okay, so we call it high disorder. Okay, so for this case, you can see that solid, liquid, and gases, when you convert from solid to liquid to gases, you actually increase the entropy of the system. Okay, so why I say that gases have higher entropy? You can imagine this as a highway. Okay, so for the solid state, all the car is moved in the same direction, very in order. Okay, so again, you want to use the road, you can transfer to your destination very, very fast because everything in order, all the car move in the same direction. Okay, but once you change the gases form, now the traffic consider is have a very high entropy. All the car move very, very fast, and then all of them come from different direction. Are you able to travel from this point to the destination easily and very fast? No, you will be hit by the surrounding car. Okay, even you can reach, you have lost a lot of energy due to some collection or hit by the car. Okay, so this we call it as a entropy in the molecule. So this entropy will actually affect the conversion of the thermodynamic process. Okay, the higher entropy, the conversion will become difficult. Okay, so this irreversibility also call it as a zero Exergy. Irreversibility equal to zero for a total reversible process with 100% efficiency. The useful and reversible work term are identical. The smaller the irreversibility associated with the process, the greater the work that will be produced, and the performance of the system can be improved by minimizing the irreversibility associated with it. Okay? Yes, we know that we want to minimize the entropy so that we can improve the system. But for a given temperature and pressure, the enthalpy for a gas is actually fixed. It's a constant. So it means that we can always know the entropy of the system by referring to the temperature or pressure of the system. Let's say for the water. For water, if I want to know the entropy, I can just refer to the steam table. Okay, and then from that, I can check temperature and pressure and what is the corresponding entropy at that condition. Okay, so from there, I will estimate how much possible losses during the conversion or during the heat transfer based on the amount of entropy in the system. Okay, because something like this entropy can be increased or decreased. Okay, if you increase in entropy, it means that you decrease in the total possible work output. Okay, so these are the cause of irreversibility in general, friction, inelastic deformation, transfer of electricity through the resistor, spontaneous chemical reaction, combustion, and magnetic hysteresis of the material. This irreversibility refers to the general irreversibility. But in terms of thermodynamics, in terms of heat transfer, the irreversibility will refer to the change of entropy. Okay, because of the difficulty to make the process happen due to the disorderly of the molecule. Yeah. Okay, now let's look about the first law of thermodynamics. Just some refreshment. Energy cannot be created or destroyed, but can be converted from one form to another. This is referred to first law of dynamics. The increase of internal energy of a closed system. Closed system here refer to the non-heat transfer in or out. Okay, is equal to the heat supply to the system minus the work done by it. Internal energy is the energy in the molecule. Okay, normally we can measure in terms of temperature. Okay, so how the increase of internal energy should be equal to the heat supply minus the work done. How much heat supply to the system and how much energy output. Okay, energy input minus energy output, you should have the increase in the internal energy. This is what we calculated based on the first law of thermodynamics, because energy cannot be created or destroyed. So the net energy increase should be equal to input minus output. No losses. And based on the first law of thermodynamics, we have the first law of efficiency. And we can call it as a thermal efficiency as well. And this thermal efficiency is equivalent to net work output over the total heat input. Okay, so in the layman term, thermal efficiency will tell us what we get. What we get is the output compared to what we put in. Okay, so thermal efficiency. So there's thermal efficiency. We put TH. Okay, there's output over input. This is a very general efficiency that we use widely. And then here we have the thermal efficiency at the reversible manner. Reversible is mean that maximum. So based on this equation, we can determine what is the maximum possible efficiency of the system. Okay, then where the equation come from here? So first, let's say for water, how to measure the energy of the water? Okay, let's say I have a water at 30, or maybe not 30, 300. Let's say the water is at 300 Kelvin. Okay, so if I want to measure the total energy of the water, should be energy, should be M C delta T. Okay, M is the mass of the water, C is the capacity factor, heat capacity of the water, specific capacity of water, and T is the temperature change or maximum temperature change. Okay, so if I want to list all the energy, the temperature change to be to 0 Kelvin. Okay, so this is my input. Agree? My input equal to MC 300. Okay, and what is my output? If reversible, it means that I try to calculate the maximum possible output. Okay, of course I cannot drop to 0, but I can drop up to the surrounding temperature. Let's say the surrounding temperature is at 280 degrees Celsius. No, let's say it's 25 degrees Celsius. So we have to convert to Kelvin plus 273. Okay, so from here I get 298 degrees Celsius. So the surrounding temperature is 298. So output should be M, C, and delta T should be 300 minus 298. So for this case, it's only the output. So the output divide input, you will get the efficiency for the reversible process. So let's say I do not want to substitute the value, I just put the amount will be input over output will be, input will be M, C, delta T will be T hot minus 0. Okay, terbalik. MC T hot minus 0. This is the input, and output will be T hot minus T low. High and low, high temperature and low temperature. So this T low is the surrounding. Okay, surrounding temperature. So output, terbalik lah. Output over input. Okay, so this is referred to the maximum possible output, and this is referred to the energy. And the top is Exergy. Okay, so the thermal efficiency at reversible process also can be equivalent to Exergy over energy. Okay, and you can see that I can just rearrange the equation to get 1 minus TL over TH. M and C are actually the same. Okay, so 1 minus TL, this TH and TH become 1 minus TL over TH. Okay, so this is the thermal efficiency at reversible manner, our maximum possible efficiency of the system. Okay, so if you measure output over input, it's already very near to this, then don't need to do any improvement anymore. Or else just waste of your effort. Okay, clear about this first law of thermodynamics? No issue, huh? If no issue, then I think second law of thermodynamics need some time to explain. Maybe we can stop here. Just have 1 minute left. Okay. Any question? No question, huh? Okay, good. So I think that's all for today. Thank you for your time and see you next week. Okay, bye-bye.
Thank you,
everyone.
sir.
Thank you, sir.
Okay, Jing Wei, yes, you need to study the concept of Exergy. It's still very important, but not need to cover the calculation part. Okay, but mechanical mecha, this one definitely one calculation for this chapter will come out. Okay, Jing Wei? Okay, good.
Thank you, sir.